Today, we're going to explore the latest updates and changes in the newly released version of Kubernetes Platform 1.30. This release is the first release of 2024 and includes 45 enhancements. 10 are new or improved alpha enhancements, 18 are beta enhancements enabled by default from this release, and 17 enhancements are stable now. My name is Mumshal Manambat and welcome to KodeKloud. A quick note to subscribe to our channel to receive latest updates on Kubernetes as and when they release. The theme for the 1.30 release is Uwubernetes. People from all around the world, from all backgrounds, build and release Kubernetes. Most of them aren't paid. They do it because it's fun, they want to solve problems, learn new things, or just love being part of the community. And many found their friends, homes, and careers through this community. The release team is proud to be part of Kubernetes' growth. The new release is for everyone who builds, releases, and maintains the systems that support Kubernetes. Hence, the Kubernetes version 1.30 is nicknamed Uwubernetes. The name combines Kubernetes with Uwu, so Uwu is an emoticon that shows happiness and cuteness, and hence this is the cutest Kubernetes release logo that's ever been. So we have selected 10 major enhancements for this release. Our first pick is container resource-based pod autoscaling feature. So this feature was first introduced in Kubernetes version 1.20 with the Kubernetes enhancement proposal 1610. It introduces something known as the container resource type metric in the horizontal pod autoscaler. And by the way, if you're not sure about what a Kubernetes enhancement proposal is, please check out this video that I did earlier about it. Now, before this update, the horizontal pod autoscaler, or HPA, used the resource type metric, which looked at the overall resource use of all containers in a pod combined. Now, for example, if you have a main application container and a sidecar container for log shipping, the HPA would calculate the CPU utilization by adding up the CPU use of each container. So if the main app container is very active, but the sidecar container, which manages log shipping, doesn't use much CPU, perhaps because the app doesn't generate that many logs, now their combined utilization might not accurately reflect the needs of the main app. However, the container resource type metric, which was introduced in Kubernetes version 1.20, focuses on the resource usage of individual containers within a pod. Now, this is helpful because each container might use resources differently and change its usage at different rates depending on the workload. For instance, using the container resource type metric, the HPA can monitor just the CPU usage of the main app container regardless of the sidecar's lower activity, and it aims to maintain an average CPU utilization of about 70% for the app container, ensuring that it has the resources that it needs without being skewed by the sidecar's usage. Now, with Kubernetes version 1.30, this feature is now considered stable and is turned on by default. Another major change in the release is the introduction of structured parameters for dynamic resource allocation. Now, we all know how the Kubernetes scheduler works. When it gets a request, it schedules a pod on a node, and it looks at certain resource requirements, such as how much memory or CPU the pod requires, and then identifies a node with sufficient free resources and assigns the pod to that node. And that is easy when we are only referring to CPU and memory. But what about other resource types, such as storage requirements? So with persistent volumes, Kubernetes supports attaching storage from external parties to a cluster. And this requires provisioning the storage, slicing it, and then attaching it to servers. And now let's look at other advanced use cases. Now, as a data center operator, a user wants to place accelerators in a separate enclosure where they can get connected to different compute nodes through Compute Express Link, for example. This is more cost-effective because not all workloads need these accelerators, and more flexible because worker nodes can be added or removed independently from the accelerators. Another use case is where, as a 5G telco operator wanting to use the FPGA IP block, signal processor, and network interfaces provided by the Intel FPGA card in a Kubernetes Edge cluster, Intel provides a single resource driver that has parameters for setting up all of these hardware functions together as needed for a data flow pipeline. This is where dynamic resource allocation comes in. It is an API for requesting and sharing resources between pods and containers in a pod. So the third-party drivers would mark the resource claims as allocated once the resources were reserved, but the scheduler lacks direct visibility into what resources were available. So this lack of insight led to scheduling delays because pods could not be scheduled until the resource drivers confirmed that the resources were allocated. Additionally, if a pod was scheduled to a node but couldn't run due to a lack of resources, it would block other resources, thereby reducing overall system performance and causing inefficiencies. With the introduction of structured parameters in version 1.30, the Kubernetes scheduler now has more active role in resource management. The scheduler scheduler can directly access a comprehensive list of available resources through resource slice objects, and these objects provide detailed information about the resources that are available, which allows the scheduler to make well-informed decisions about resource allocation. So the streamlined process involves the scheduler using structured parameters within the resource claims to directly allocate resources, reducing the need for extensive communication with resource drivers. This change leads to faster scheduling of pods and minimizes the delays previously caused by the back and forth communications, thereby reducing resource blocking and enhancing overall scheduling efficiency. So here's an example of a YAML configuration for a resource claim that is tailored for specific GPU resources. So this configuration clearly specifies the GPU model and capacity, enabling the scheduler to efficiently match the resource within the pods that require specific GPU capabilities, thereby streamlining the scheduling process. The dynamic resource allocation, or DRA, was introduced in Kubernetes 1.26 release and still is in alpha stage. Next, we look at node memory swap support feature, which is in beta stage. Originally, Kubernetes disabled the swap memory feature by default. The swap memory, often simply called swap, acts as an overflow area that your computer's operating system can use when the RAM, or the random access memory, is full, and you probably know this already. So when the physical memory, RAM, is not sufficient to handle the current tasks, the operating system temporarily moves some data from the RAM to a designated area on the hard drive or SSD known as the swap space. And this process allows the system to free up RAM for new tasks that need immediate attention. But what does that have to do with Kubernetes? So in the context of Kubernetes, enabling swap memory management allows nodes to start using the swap as an extension of RAM. Now, since swap memory was disabled by default in Kubernetes, if nodes' memory become exhausted, there was no fallback to swap. And this could potentially lead to system crashes or pods being killed, which is not ideal for stability. Now, on the other hand, enabling swap through the node swap feature gate used the unlimited swap behavior by default. So this behavior allowed pods to use unlimited swap memory, which could compromise node performance and lead to less predictable system behavior. So unlimited swap could result in excessive swapping, which slows down the system because disk access speeds are typically much slower than memory access speed. To address these issues, Kubernetes version 1.30 introduces significant changes to how swap memory is managed on Linux nodes. It's important to note that swap support is available only on Linux. Now, by default, Kubernetes version 1.30 operates in no swap mode. This mode supports running on a node where swap space is active, but ensures that pods do not use any of the swap space. Now, this setup is beneficial for systems where swap presence is required by other system processes, but should not be accessed by Kubernetes pods. Now, to enable a node to operate in this mode, you need to set the following kubectl configuration, or you can even set the fail swap on command line flag to false. Now, this configuration ensures that the kubelet can run on nodes with active swap space without allowing pods to use it. Now, the most notable addition in version 1.30 is the limited swap mode. Now, this mode allows pods to use a limited amount of swap space up to the memory limits set for each pod. And this approach prevents any single pod from consuming excessive swap, thus maintaining better control over system performance. Now, limited swap is ideal for environments where some degree of swapping is acceptable for better overall memory utilization without compromising the node stability. So here is how you can configure a node to use limited swap, and you can refer to the documentation for a detailed explanation, but the general concept is similar to what we have explained. The next one on our list is structured authorization configuration feature, which is graduated to beta. This release brings improvements to the structured authorization configuration, which we first introduced in the last Kubernetes release version video, the 1.29 release. And this feature is now moving to beta and is enabled by default. Now, for more information on the structured authorization configuration, please watch the Kubernetes 1.29 release video that we released a few months back. Now, from Kubernetes 1.30 onwards, managing authorization settings through a configuration file is much simpler. So the configuration file format has reached beta level maturity and can be activated by simply specifying the authorization config command line argument like this. Now, this change eliminates the need for enabling specific feature gates as they are now enabled by default. In this release, the structured authorization configuration has been enhanced to support dynamic reloading and detailed metrics reporting as well. With a dynamic reloading feature, the Kube API server now actively monitors the authorization config file for any changes, and whenever the file is modified, the API server automatically reloads the configuration without needing to restart. And this capability is crucial for maintaining seamless security protocols while making adjustments. Metrics related to these reloads are captured under the API server authorization config controller automatic reload last timestamp seconds metric. The metric tracks the timestamp of the last reload and labels it with status equals success for successful updates and status equals failed for any issues encountered. And if a reload fails, the API server continues using the previously loaded authorization configuration, ensuring stability. Also, enhanced metrics metrics are now reported for authorization decisions. So the API server authorization decisions total metric provides insights into the total number of authorization decisions made, categorized by authorizer type, name, and decisions reached. And this detailed metric helps administrators understand the effectiveness and responsiveness of their authorization configurations. Another major update is supporting user namespace in pods, and that feature is moving to beta. So in our last release video, we introduced the feature of user namespaces in pods for Kubernetes, discussing its initial capabilities in version 1.29. And if you haven't seen that discussion or need a refresher on the foundational concepts, you can watch it here before continuing with the new updates in version 1.30. But with Kubernetes version 1.30 release, we see further enhancements to how user namespaces are managed. So this feature has now moved to beta and offers more detailed control over how user IDs and group IDs are handled by the kubelet. Now we have the ability for administrators to specify exact ID ranges that the kubelet should use when creating user namespaces for pods. And this improvement is particularly important for security because it prevents the overlap of UIDs and GIDs between the host and the pods. So overlapping IDs can lead to security risks such as unauthorized file accesses, so that this capability helps keep your cluster secure. Now, the default behavior of the kubelet assigns UIDs and GIDs above the typical range used by host systems. So that's 0 to 65,535. And this is based on the assumption that the host files and processes use UIDs and GIDs within this range. So a common setup for Linux distributions. By assigning pod-specific IDs beyond this range, Kubernetes ensures that there is no conflicts between the pod and the host IDs, which helps to protect the host from potential vulnerabilities exploited by pods. To use custom UID and GID ranges for pods, your system needs to meet certain criteria. So you must have a kubelet user setup on your system, the get sub IDs utility installed, which is part of Shadow Utils, and the correct entries in the etc sub ID and etc sub GID files. These entries dictate how many UIDs and GIDs the kubelet can allocate to pods and must be configured carefully to avoid any overlaps with other IDs used on the system. For example, here's how you might set up the necessary files. So this setup gives the kubelet over 7 million UIDs and GIDs, starting at 65536, to manage pods safely without risking overlap with the host IDs. And here's a sample YAML example that shows how to configure a pod to use specific UIDs and GIDs within the safe range. Now, this run as user setting specifies that all processes within any containers in the pod will run with a user ID of 100,000. Similarly, the setting run as group 100,000 dictates that the primary group ID for all processes within the containers of the pod will be 100,000. Another major addition to the 1.30 release is SELinux label optimization, which is introduced as an alpha feature under a new feature gate named as SELinux mount. So SELinux, or Security Enhanced Linux, as you already know, is a security architecture integrated into various Linux distributions. So SELinux operates on the principle of least privilege, where every process and system resource has only the permissions necessary for its function. In Kubernetes, SELinux can enhance the security of pod execution by ensuring that each pod complies with security policies specified by the SELinux context on the host system. So this integration helps to isolate pods from each other and from the host, minimizing potential security breaches. Now, suppose you have a Kubernetes cluster where you want to ensure that certain pods run with a specific SELinux level to access a sensitive volume securely. Let's look at how you can define this in a Kubernetes pod specification. So this is an example of a YAML configuration for a pod that specifies SELinux settings for enhanced security. In this configuration, the SELinux options is specified at both the pod level and the container level. So this setting ensures that the SELinux context is enforced for all processes running within the Nginx container. And the volume, secure volume, is mounted at /data, which is meant to be accessed with the same SELinux context, ensuring that the data handled by this container complies with the defined SELinux policies. So let's have a quick look at how SELinux works in this scenario. So every file, directory, and process within the pod is labeled with the specific SELinux label, which defines its security context. Now, when the Nginx container tries to access or modify files within the data directory, the SELinux policy on the host checks the label of these files against the container's SELinux context. The access is permitted only if the policy allows interactions between these labels, and if the container attempts to perform an operation that is not allowed by the SELinux policies, the action is either logged as a violation or outright denied based on the policy rules, and this ensures that unauthorized actions are caught and handled appropriately. Next, we have job success or completion policy that was introduced as an alpha feature. So with the introduction of the job success completion policy in Kubernetes version 1.30, Kubernetes now offers enhanced flexibility for executing batch jobs, particularly beneficial in complex fields like machine learning and scientific research. Traditionally, Kubernetes jobs, especially indexed jobs, were only considered complete when all pods or indexes succeeded. So in Kubernetes, an indexed job allows each pod within the job to be identified by a unique sequential index. And this setup is beneficial for tasks where each pod performs a distinct function or when pods need to coordinate efforts. And the unique index of each pod helps define its role within the larger job, aiding in the organization and the coordination of the whole task. So this all or nothing approach was not efficient for jobs where only specific tasks, often performed by key pods known as leader indexes, needed to succeed or the job's overall objective to be fulfilled. For instance, in distributed applications like MPI, Message Passing Interface, and PyTorch, the leader pod, often at index 0, might be responsible for compiling and processing the output from other worker pods. And if the leader pod successfully completes its task, there might be no need to wait for all worker pods to finish, which previously led to unnecessary consumption of computational resources. So the job success completion policy allows for defining custom success criteria for indexed jobs. This feature supports scenarios where job completion can be declared based on the success of specific indexes, particularly beneficial when the focus is on pods with critical roles known as leader nodes or leader indexes. So here's how the feature works. Users can specify conditions under which a job should be considered successful. This might include the success of one or more specific pod indexes, such as the leader index or a count of successful pods. Once the defined success criteria are met, Kubernetes can terminate lingering pods that are no longer needed, which helps in freeing up resources and reducing costs. Now, when a job meets the defined success policy, a new condition, success criteria met, is added to the job status, and this indicates that the job has completed successfully according to the specified policy. Now let's take a scenario. A machine learning researcher is primarily concerned with the output from the leader pod in a distributed training job, and this pod is launched as index 0 and plays a pivotal role in the job's success. In this configuration, the job is marked as successful when the leader pod at index 0 succeeds. Subsequent pods are terminated to conserve resources. Now, in another scenario, a researcher needs the job to be successful when either the leader pod, which is index 0, succeeds, or a specific number of worker pods complete their task successfully. And this setup acknowledges the critical role of the leader index and the additional flexibility with worker indexes. This example, the job is considered successful if either the leader pod at index 0 or any 5 of the worker pods indexed from 1 to 9 succeed, and this allows the job to conclude efficiently once critical computations are completed. Next on our list is interactive mode for Kubectl delete command, which is now moved to stable. So the Kubectl delete command is, as you can imagine, a potentially disruptive tool within the Kubernetes ecosystem, capable of irrevocably removing critical resources. Recognizing the need for enhanced safety measures, Kubernetes version 1.28 introduced an interactive mode for this command, which has now graduated to stable in the latest release. Now, prior to this enhancement, using Kubectl delete post risks due to its irreversible nature. For example, a simple typo could result in deleting all persistent volumes instead of just the persistent volume claims within the namespace, potentially causing significant data loss and operational disruptions. To mitigate the risk of accidental deletions, Kubernetes now, from a 1.28 release, includes an interactive mode that can be activated using the interactive or the -i flag with the Kubectl delete command. And this feature enhances user control in two ways. First, it is previewing deletions. When the interactive flag is used, Kubectl first displays all the resources that are about to be deleted, providing a clear preview to the user, and also confirming actions. After listing the resources, as you can see, it prompts the user to confirm the deletion by typing Y. Yes, if the user responds with N or no or any other input, the deletion process is cancelled and the resources remain intact. Let's now have a look at the routing preferences for services, which is introduced as an alpha feature. Previously, Kubernetes did not offer a straightforward way to influence how traffic is distributed among service endpoints across different zones. Traffic would generally be distributed across all available endpoints in the cluster without regard to their geographic or network proximity to the request source. Now, this often led to inefficient routing, increased latency, and higher cross-zone networking costs, and there was no predictable method method to ensure traffic would preferentially route to the closest available endpoint. Now, the introduction of the traffic distribution field allows users to specify preferences for how traffic should be routed to service endpoints. So the primary mode introduced under this field is prefer close, which instructs implementations like Kubectl to prioritize sending traffic to endpoint within the same zone as the client. If no endpoints are available in the client's zone, traffic is then routed cluster-wide. Consider a Kubernetes service configured to use the prefer close routing preference. In this configuration, the service is set to route traffic preferentially to pods in the same zone as the client. If no pods are available in the same zone, Kubectl falls back to routing traffic to available pods in other zones. But how does that work? How does Kubernetes know which pods are in which zone and where to route traffic to? So let's walk through a scenario. Imagine we have an online retail application deployed on a Kubernetes cluster that spans 3 zones in a cloud environment: Zone A, Zone B, and C. Now, our application is structured with multiple microservices, one of which is, say, the product catalog service. And this service is critical as it handles requests to fetch details about products. Now, the Kubernetes nodes in our cluster are automatically labeled by the cloud provider with their respective zones. So it could be something like zone equals A, zone equals B, zone equals C, etc. So for the clusters that are not hosted on cloud infrastructure, administrators need to manually label the nodes with topology information to ensure prefer close can function properly. Now, in our case, product catalog service is deployed across all 3 zones to ensure high availability and resilience. And the service configuration is configured so the prefer close flag is set to true. So let's have a look at how the prefer close works in this setup. Now, when the product catalog service is deployed, Kubernetes' endpoint slice controller creates endpoint slices for the service, and each endpoint slice contains information about the endpoints, pods that are running the service, including their IP addresses and additional metadata like their zone. Now, alongside the basic endpoint data, the endpoint slices include hints that direct traffic preferences. So in this scenario, the hints would indicate a preference for routing traffic to endpoints within the same zone. When a user from Zone A accesses the product catalog service, the Kubectl running on their node reads the endpoint slice for the service. Noticing the prefer close setting and the associated hints, Kubectl routes the request to an endpoint also located in Zone A, and this minimizes the latency since the traffic stays within the same zone and reduces cross-zone data transfer costs. So if for any reason all pods in Zone A are unavailable, Kubectl will then route the traffic to available endpoints in Zone B or C, and this ensures that the service remains available even if one zone faces issues. Now, another important thing to note is that the spec.traffic distribution field is designed to complement existing traffic policies like the external traffic policy and the internal traffic policy. So if these policies are set to local, they take precedence over the prefer close setting for the respective traffic type, external or internal. So if set to cluster, or if not set at all, the prefer close preference guides the routing behavior. Now, apart from the above-mentioned highlights in K's 1.30 release, there are several features that have graduated to stable that we have already discussed in the last releases like 1.29, 2.8, and 2.7. So let's look at some of the major ones that we discussed in our previous release videos and now are stable and in beta. So one is reduction of secret-based service account tokens, which now moved to stable. The CEL for admission control is now stable. Node log query is now in beta. CRD validation, which is in beta. And if you want to know more about this release, go to the following links that are shown below. Well, that's all for this video. I hope you found this valuable. If you liked the video, don't forget to like and leave a comment below. Let us know what you like, what you don't like. If you'd like us to create more videos like this on specific topics, let us know in the comments and we'd be happy to create them. Do subscribe to our channel because we release similar videos every week. Also check out KodeKloud website as we release new courses and new learning experiences. Thank you so much for being part of the community, and I'll see you in the next one.